Earth is not as alone as we once thought. For millennia, we have looked up to a single, constant moon, but our planet sometimes hosts other, more temporary companions. In late 2025, astronomers confirmed the presence of just such an object. It is a small body, now designated 2025 PN7. News headlines were quick to label it our second moon. While this description captures a sense of wonder, the reality is far more intricate and, in many ways, more fascinating. This small visitor does not orbit our planet in the traditional sense. Instead, it is engaged in a complex and delicate dance with Earth as they both journey around the Sun. The discovery of 2025 PN7 serves as a profound reminder of the dynamic nature of our solar system. The space around our planet is not an empty void, but a busy thoroughfare of celestial objects. This newly identified object is what scientists call a quasi-moon, a quasi-satellite. It is a temporary companion, bound not to Earth itself, but to Earth's orbit. Its path is a looping corkscrew-like trajectory that keeps it in our general vicinity for a time. The identification of an object like 2025 PN7 is a meticulous process, born from patience and precision. It began not with a single dramatic moment, but with the tireless work of automated sky surveys. These powerful telescopes scan the heavens night after night, cataloging millions of points of light. Within this river of data, astronomers search for faint objects moving against the backdrop of distant stars. 2025 PN7 first appeared as just such a faint, unassuming dot. Its slow, unusual movement, relative to other near-Earth objects, immediately flagged it as an object of interest, prompting a coordinated follow-up campaign by observatories around the world. Once the initial detection was made, the real work began. Astronomers needed to track the object precisely over many nights to chart its course. Large telescopes were pointed towards its predicted location, capturing images, to refine its position, to refine its brightness. This crucial data was then sent to organizations like NASA's Jet Propulsion Laboratory, JPL, and the Center for Near-Earth Object Studies, CNEOS. There, powerful computers ran complex simulations, fitting the observational data into orbital models. These models are what ultimately revealed the object's true nature. So, what exactly is a quasi-moon? The term describes a specific type of co-orbital relationship an object can have with a planet. Unlike a true moon, which is gravitationally bound and orbits the planet, a quasi-moon orbits the Sun. Its orbital period around the Sun is nearly identical to that of the planet it accompanies. For 2025 PN7, this means it takes about 1 year to complete a full circuit around our star, just like Earth. This shared rhythm locks it into a synchronized dance that can persist for a very long time. From our moving vantage point on Earth, 2025 PN7 appears to trace a slow, looping path around us. It looks like it's spiraling lazily around our planet over the course of a year. This is an illusion. In reality, Earth and 2025 PN7 are moving together, like two runners on adjacent tracks of a vast cosmic stadium. The quasi-moon's orbit is slightly more elliptical than Earth's. That means at different points it moves slightly faster or slower than our planet. The speed difference makes it drift ahead of Earth, then fall behind, tracing a looping pattern from our perspective. The gravitational interplay governing this motion is incredibly delicate. The Sun remains the dominant gravitational influence on 2025 PN7, keeping it in solar orbit. Earth's gravity, however, provides gentle but persistent nudges. As the quasi-moon drifts closer, Earth's gravity tugs on it, subtly altering its path. These gravitational perturbations prevent it from drifting too far away. They act like invisible tethers, keeping its looping dance nearby instead of letting it escape. This relationship is not permanent. Over centuries or millennia, cumulative gravitational pulls from other planets will disrupt the balance. Jupiter, Venus. Eventually the synchronization will break and 2025 PN7 will wander away from Earth's co-orbital path. For now, it remains our temporary companion. Its presence is a real-world laboratory for studying multibody gravitational dynamics, a puzzle since Newton's time. It's a wonderful chance to learn. While the discovery of 2025 PN7 is exciting, it is not the first time we have found an object sharing our orbital space. Earth has had several known quasi-moons and other co-orbital companions throughout its history. One of the most famous examples is an asteroid named 3753 Cruithne. Discovered in 1986, Cruithne follows a much more complex and elongated path known as a horseshoe orbit. From Earth's perspective, it appears to travel towards our planet, then reverse course just before reaching us, tracing a massive bean-shaped path that avoids our planet while sharing its average orbital distance from the Sun. Another notable companion is the asteroid 2016 HO3. This tiny object, likely no more than 100 meters across, followed a looping path quite similar to the one projected for 2025 PN7. For nearly a century, 2016 HO3 remained a steadfast, albeit distant, companion. It would drift ahead of Earth and then fall behind. But our planet's gravity always kept it from straying too far. Its dance was a perfect illustration of the stable, long-term nature that some of these quasi-satellite relationships can achieve before they eventually decay. More recently, astronomers identified 2023 FW13, another object whose orbit is influenced by our planet. The dynamics of these objects can vary significantly. Some, like 2016 HO3, perform a relatively tight, corkscrew-like dance. Others, like Cruithne, engage in a much wider, more chaotic-looking horseshoe pattern. Comparing the specific orbital characteristics of 2025 PN7 to these other known quasi-moons is a crucial step for scientists. Each one provides a new data point, helping to refine our models of how these temporary captures occur and how stable they can be over time. By studying this growing family of co-orbital objects, scientists can better understand the population of asteroids in Earth's neighborhood. These objects are a diverse group, each with a unique history. Some may be fragments from asteroid collisions far away, while others might originate from closer to home. Each new discovery, including 2025 PN7, adds another piece to this complex puzzle. They are not just curiosities. They are clues to the formation and evolution of our solar system, offering a window into the subtle gravitational web that connects all celestial bodies. The concept that keeps objects like 2025 PN7 bound to our vicinity is known as orbital resonance. In simple terms, this occurs when two orbiting bodies exert a regular periodic gravitational influence on each other. In this case, 2025 PN7 and Earth orbit the Sun in a near one-to-one resonance, meaning they both complete one orbit in almost the same amount of time. This shared rhythm is the foundation of their entire relationship. It ensures they repeatedly encounter each other in a predictable pattern, letting Earth's gravity manage the smaller object's path. Imagine pushing a child on a swing. To make the swing go higher, you must push at the right moment in its cycle. This is resonance. Likewise, Earth's gravity gives 2025 PN7 tiny pushes or pulls at regular points in its orbit. Those nudges prevent escape, but aren't strong enough to make it a permanent moon. The result, a stable, self-correcting system. If the Quasi-Moon drifts too far ahead, Earth's gravity slows it down. If it falls too far behind, it gets a tug that speeds it up. So why does this matter to us? Quasi-moons like 2025 PN7 are scientifically invaluable. Firstly, they're natural laboratories for testing celestial mechanics. Predicting their long, complex orbits requires incredibly precise gravity models. Each observation helps astronomers refine models for navigating spacecraft. Each observation helps astronomers refine models for predicting potentially hazardous asteroids. They're a low-stakes way to test our predictive limits in complex gravity. Furthermore, these quasi-moons are attractive targets for future missions. Because they move at velocities similar to Earth's, they require relatively little fuel to reach. Travel to one, orbit it, retrieve a sample. Such a mission could reveal the composition of small asteroids. Studying 2025 PN7 up close could tell us about the solar system's building blocks. For now, this fleeting visitor is a gift, a cosmic coincidence that deepens our understanding and inspires exploration. As we watch this faint speck of light trace its elaborate path, we are not just observing a rock in space. We are witnessing a living example of the fundamental laws that govern the universe. It is a quiet spectacle, unfolding on a scale almost too vast to comprehend, yet it is happening right here, in our own celestial backyard. It's quietly astonishing.